Okay, so in this lecture, we are going to learn about pruning and sparsity, which is a very fundamental technique for efficient deep learning. So in this lecture, we will first introduce neural network pruning, okay, which can reduce the number of parameters in neural networks. Sometimes it can even reduce the number of parameters by 90%, right? Only keep 10% of the parameters. And how do we recover the accuracy, right? And which parameters should we remove and which parameters should we keep? So we are going to learn those techniques in order to improve the computation efficiency, since we will have a much smaller model, right? Much less memory movement and a more efficient inference. Okay? We are going to go through different steps of pruning, introduce different pruning granularities, different criterions of neural network pruning. Okay. So first, some motivation. Today's AI is getting super big. This is the natural language processing. The NLP model size is increasing exponentially in recent years. So model size is basically the number of parameters in billions. Another important concept is that the memory is much more expensive than computation, right? So more data movement means we need to do more memory reference, which will lead to a higher amount of energy consumption. So this table shows the energy for different operations, like a 32-bit add consumes only 0.1 picojoules. Okay? A 32-bit float add takes about 0.9 picojoules. Okay? Accessing the register file, that takes about 1 picojoule. They are both pretty small. Multiplication, 3 picojoules. Accessing cache, 5 picojoules. But accessing the DRAM memory, 640 picojoules, right? Super expensive. So it is those data movement from memory that is draining the battery of our mobile devices, right? So we want to make the memory movement as little as possible, right? So in order to do that, what are the possible methods you can think of to reduce the data movement and memory access? You can think of it from multiple perspectives, right? From the algorithm perspective, what if we just reduce the model size, reduce the activation size, reduce the workload, right? And then from the system's perspective, we can build more efficient hardware or better compilers with better scheduling policy, right? To encourage more locality, so we can put as much as data to make them stay in the cache rather than having to access the DRAM, right? So these are the two methods. In this lecture, we will learn about the first method from the algorithm perspective. How do we fundamentally reduce the requirement for data movement? And if you're interested in the hardware approach, welcome to take the hardware deep learning course in the next semester, which is an awesome complementary to today's lecture. Okay. All right, so this is today's agenda. Let's start with what is pruning. Okay. So pruning naturally happens in human brain. Okay. So from this study by Peter Hartenlacher, so a newborn child has about 2,500 synapses per neuron, right? And when the child becomes 2 to 4 years old, this number surges very quickly to 15,000 synapses per neuron. Okay? That's a lot of growth when the baby is growing. However, when he or she gets to adolescence, this number didn't keep increasing, but started to decrease. Okay? And until the adult, like us, roughly 7,000 synapses per neuron. It's still more than a newborn child, but it's definitely smaller, half times smaller than when the child is 2 to 4 years old. Okay, so this pruning naturally happens in the human brain. When we are developing our brain, those important connections get capped, and those unimportant synapses get pruned away. Okay? And does that happen to deep neural networks? The answer is yes. So we can make neural networks smaller by removing some of the synapses and some of the neurons. Okay? So turning a dense neural network into a sparse neural network. Okay, so we can prune both the synapses and also the neurons. So this is a high-level overview. And then how exactly are we going to do pruning? Okay, so we first train this model to convergence. We have to first train the model to recognize which neuron is important, which neuron is not important. Okay, and then this is the suppose this dashed line is the baseline accuracy, right? And then we are going to prune away some of the connections. And the more we prune away, okay, you can see the less the accuracy. When we are pruning away 80% of the parameters, the accuracy drop is actually pretty significant, 4.5% drop of accuracy. Okay, probably 50% is okay, right? When we are pruning 50% of the parameters, we still have an accuracy drop that less than 0.1%. Okay, and on the bottom plots the weight distribution, okay, before and after pruning. So before pruning, it's roughly forming a normal distribution for the weights for this particular layer. Okay, and after pruning, we are removing those small parameters. Okay, so you can see if the value, if the weight's absolute value is below a threshold, then we are going to remove those connections. Okay, and you can imagine the more we remove, the larger this gap, since we are pruning away more parameters. So this is too bad. The accuracy is dropping very significantly. How can we recover the accuracy? Okay, so we can train the remaining weights. Okay, say we prune away 80% of parameters. You still have 20% left, right? What about you just train those survived 20% of the parameters? Okay, so we can train them using a smaller learning rate, since they already converged almost, and we can actually recover the accuracy. No accuracy loss by retraining those 20% of surviving parameters. Okay, so which is pretty good. And after retraining, we plotted the weight distribution again. Still, it roughly follows this trend, but becomes softer, smoother, since we are retraining those weights. So is that the limit? Okay, can we prune more than 80%? Actually, we can do this process iteratively, right? So we prune some parameters, we retrain the remaining parameters. We prune a little bit more, and then we retrain again, right? So by iteratively doing such pruning and retraining, actually we can remove 90% of AlexNet without losing any accuracy. This is wonderful, right? And after that, the accuracy begins to drop very quickly. Okay, so this is the high-level idea of the pruning process. So how much can we prune for these modern neural nets? So I tried AlexNet, VGG, GoogleNet, ResNet50, SqueezeNet. Before pruning, the number of parameters of AlexNet and ranges from these neural nets ranges from 60 million to 1 million, right? So SqueezeNet is a super compact, super small neural nets, right? That I designed in collaboration with Berkeley during my PhD, but it has only 1 million parameters, right? AlexNet is very classic 61 million parameters. So after pruning, it becomes only 6.7 million. So that's 9 times reduction. And the computation can be reduced by 3 times. Okay. Why the number of the reduction for max is different from the reduction of the number of parameters? They have different calculation, right? Remember, in the last lecture, we described how to calculate the number of parameters versus the number of max, right? For a convolution layer, what is the number of parameters? It is the kernel size times the kernel size times input channel times output channel, right? And for the max, that is the multiplication of 6 terms, right? How many pixels you have to calculate? That is output resolution height times output resolution width and times the channel of the output. And how many arithmetic operations we have to do per pixel? So that is kernel x, kernel y times the input channel. So altogether, you have to multiply 7 terms together, right? So they have different calculations. Therefore, the reduction of the number of weights is different from the reduction of the number of max, right? And for the VGG, after compression is only 10 million, roughly 10 million parameters, 12x reduction. So this model originally it is much larger. So you can imagine it also has a larger compression ratio compared with AlexNet. For GoogleNet, this appeared after these models, which initially is more compact. It has 7 million parameters. So even multiplied by 4 bytes per weight, if you use a 32-bit floating point, that's only 28 million parameters, okay? 28 megabytes, right? So after pruning, it becomes only 2 megabytes. So about 3.5x reduction of the number of parameters. And ResNet, very popular, 26 million parameters, about 3x reduction. And the common observation here is that for these modern neural nets, which is fully convolutional neural nets, right, they have no FC layer, and therefore there's less redundancy to begin with. Okay, and for this AlexNet and VGG, they both have a very bulky fully connected layer, okay, which occupies a huge amount of number of parameters. So that's something we should avoid when you are designing compact neural nets for these microcontrollers or for these mobile devices. Try to use those fully convolutional neural networks to begin with, and then followed by these model compression techniques. Okay. So the exciting thing is the SqueezeNet. So when I was in my 4th year of PhD, work on this project, initially it has only 1 million parameters. So we were thinking, oh, it's already super compact. Is that the limit? Can we further prune it, reduce it? So I started the experiment, and actually, this neural net is also compressible, okay, without losing any accuracy. So we reduced the parameters from 1 million to only 380K. Okay, that's about 3x reduction without losing any accuracy, which is pretty exciting. So in later part of this lecture, we will teach how to design these efficient architectures to begin with, okay, and then followed by these model compression techniques to further compress it. So that's the flow which is widely adopted these days. First, design a small and compact neural net like SqueezeNet. You can tell from the name, SqueezeNet is pretty small. Okay? And then prune, quantize, compress these small neural nets. That's a good practice. Okay, and let's go to a question.
Does this method have the real-time speed up or memory saving? Because I think if you prune the matrix, the matrix becomes sparse matrix, and you need sparse matrix qualification to do real-time forwarding. So does this work as in real-time speed up or memory saving?
Yeah, we are going to cover that later part of this lecture when we are talking about the granularity of pruning. So Guangxuan asked a very good question. Since this is fine-grained pruning, we are pruning individual weights. Okay, that needs specialized hardware support like efficient inference engine, EIE, etc. But on your mobile phone, Samsung phone actually support such kind of fine-grained sparsity in their NPU. Samsung NPU support such acceleration. So from here to here, you will have measured speed up. But on NVIDIA GPU, this method doesn't have, but you have to enforce this 2-to-4 sparsity, which can enable speed up. We will talk about 2-to-4 sparsity also in this lecture. But you can save the storage if you want to upload your model to the Apple Store. This model is definitely smaller. Okay, any more questions for these results? Okay, good. So let's see what is happening to the pruned neural network. So this is an example for neural talk, which is basically image caption. So image caption is basically first do the feature extraction on the image, and then you get a vector embedding of this image, and then you feed this vector embedding to a LSTM, okay, and then generate a sentence describing what's happening in the image. So that's called image caption. So this baseline, given this image, the baseline model, the full neural network, I make a prediction saying a basketball player in a white uniform is playing with a ball. It's pretty accurate. And after pruning 90% of the parameters, it says a basketball player in a white uniform is playing with a basketball. I feel like it's more accurate than just saying playing with a ball. This is basketball, right? We suspect this is getting rid of some of the overfitting and truly having a more concise representation, extracting better features from the original image when you are pruning away the right amount of parameters. And let's see the second example. A brown dog is running through a grassy field versus pruning away 90% of the parameters. It says a brown dog is running through a grassy area. It's pretty much the same. What about the third one? A man is riding a surfboard on a wave versus pruned version says a man in a white suit is riding a wave on a beach. But we can't prune too aggressively. Say for the last image, original model says a soccer player in white uniform, a soccer player in red is running in the field, versus the pruned version says a man in the red shirt and black and white black shirt is running through a field. It's kind of getting drunk, right? So meaning that we can't prune too aggressively, which will hurt the performance of the neural net.
Is there any theory into what the optimal pruning number is, or is it entirely empirical, or anything like upper bounds?
Yeah, so this is a pretty hot research area these days to find what is the limit, what is the theoretical guarantee how much we can prune. But so far, a lot of the research that's working based on this kind of empirical study, right? We'll introduce a later part of this lecture, how do we decide how much parameter should we prune for each layer through this sensitivity analysis. So this method you can see is getting quite popular in recent years. This is showing the network. If you search the keyword network pruning, and this is the amount of publications in the number of, with respect to the number of years. Initially, the earlier paper from Professor Yang Kun called Optimal Brain Damage, that's from 1990s. And gradually, people are generating publications. And I wrote this article in 2015 in NIPS. And then suddenly this trend is getting exponentially increasing. The number of publications in the past 8 or 7 years is 3 times the number of publications in the past 30 years. So this method is widely adopted by industry these days. If you have an Android phone running some AI applications with TensorFlow, it's highly possible that you are running some of the compressed model. And also it's adopted by industry like NVIDIA, right? So just now Guangqun asked the question, can we accelerate the compressed model, right? So NVIDIA now supports this 2-to-4 sparsity, turn a dense matrix into a sparse matrix, but with the constraint that 2 out of 4 parameters has to be 0, which we are going to introduce deeper. And it can boost the performance by up to 2x on the NVIDIA Ampere GPU and after. Okay, so it introduced this A100 sparsity optimized tensor core to be able to have measured speed up. It's actually 1.5x measured speed up on BERT without losing any accuracy. And here are some of publications that accelerate the sparse and compressed neural net. So ranging from, this is part of my PhD thesis, how do we directly accelerate the sparse and compressed neural nets in hardware without having to decompress it? Okay. This method is also part of adopted by Xilinx, the FPGA company. Okay, so we can reduce the model complexity by 5 to 50x with minimal accuracy impact, and can use this tool through this Xilinx Vitis AI toolkit. Okay, now part of AMD, to compress the model before using FPGA to accelerate that. All right, so we have seen some basics of pruning and how should we formulate pruning. So in general, when we are training neural networks, we try to minimize the loss function by doing SGD on the weight. Okay, I assume everyone is familiar with SGD. But with pruning, we have a constraint, right? We have to limit the number of parameters to be smaller than a threshold. Okay, so we want to make sure the number of parameters is smaller than n in this case, right? So traditionally, we are just training the weights. Now we have a new constraint. The number of non-zero weights has to be smaller than a threshold. Okay, so L is basically representing the loss function. The x is the input weight, w is the original weight, wp means the pruned weights. Okay, and this calculates the number of non-zeros in wp, and n is the number of target non-zeros. Okay, so we can prune at different granularities, right? So if you have some basic knowledge about the parallel hardware design, right? So modern GPUs or other accelerators with high parallelism usually requires very regular computation, right? You want to compute a chunk of pixels rather than like individual pixels, so that you can keep the GPU full rather than making it starving, making it hungry, right? So there's a trade-off between how much we can prune versus whether the pruned model is more regular, right? We can, of course, prune individual weights without any regularity, or we can prune some chunk of weights. Okay, like in this case, we are pruning this entire 2x2 square, right? So that the resulting weight matrix have some pattern. Okay, so what pattern should we prune those neural networks, and what is the trade-off to balance the number of weights you can prune away versus the actual speed up? How easy you can achieve speed up on a off-the-shelf hardware versus specialized hardware. Okay. So next we're going to talk about the pruning criterion. There's so many weights, so many activations. So which one should we keep? Which one should we remove? And the pruning ratio. So like these 3 layers, do we prune 30% or 50% or 70%? How much should we prune to balance the accuracy versus model size? And finally, how do we fine-tune the remaining parameters, those survival parameters, to recover the performance? Okay. So let's start with determining the pruning granularity. Okay. And then discuss the trade-off between this structured versus non-structured pruning. So this is an example for a 2D weight matrix. So this is a 7x7 weight matrix. Originally, everything is dense. Now we prune away some of the weights, which is in white after pruning. Okay? This is purely unstructured pruning, where there's no pattern at all. It is very flexible, since we can prune away whichever weight. You can prune this one, this one, this one, any weights. Very flexible. But this is hard to accelerate on GPUs because this is very irregular. In order to store this matrix, you not only have to store those weights, but also their positions, right? Either using the COO format, giving the X and Y index, or using like CSR, CSC format, using those sparse representations. So there's overhead. However, with specialized hardware, you can build a hardware accelerator that directly run on this sparse matrix vector multiplication. For example, the efficient inference engine is the first work that can accelerate such sparse neural network after pruning. And the advantage of this method is that you have full flexibility to decide which weight to prune, right? Therefore, the pruning ratio is pretty high. And if you target just reducing the model size, this is probably a very attractive approach. On the right-hand side, we have other approaches like coarse-grained or structured pruning. Okay, so in this example, we are pruning away the entire row. Okay, the third row we are completely pruned, fourth row completely zero, so that we can condense this weight matrix from originally 7 rows into only 5 rows. Sorry, initially it was 8 rows. Now it is only 5 rows. Okay? So using such coarse-grained or structured pruning, actually we can reduce the actual computation before feeding, when we are feeding the computation to the GPU or the hardware, right? So initially we have to do this 8 by 8 matrix times a 8 by 1 a vector. Now we just pass it through a 5 by 8 matrix multiplied by a 8 by 1 vector. Okay, so we can achieve real easily get a speed up on this off-the-shelf hardware without having to design specialized hardware accelerators. However, you can imagine this is not that flexible, right? If we prune, we have to prune the entire row, right? Then it hurts accuracy. The accuracy degradation will be stronger than such pure fine-grained pruning method. So there is a trade-off. This one is easier to prune, but harder to accelerate. On this side is easier to accelerate, but harder to prune. So in order to do a detailed analysis, let's first review those terminologies, right? CI is basically the input channels. CO is the output channels. KH is the kernel size of the height. KW is the width of the kernel size. Okay, so we have these 4 dimensions, which give us many choices to select different pruning granularities for convolutional neural nets. So in this example, the KW and KH are both 3, right? Since we have a 3 by 3 convolution. CI in this case is 2. We have 2 input channels, okay? And CO in this case is 3. We have 3 output channels. We can have this full spectrum of different pruning granularities from this fine-grained pruning method, where we are free to prune these individual weights. Okay, any weights can either be pruned or unpruned. Okay, so the number of possibilities is 2 to the power of number of elements, right? Or we can have pattern-based pruning, just like Tetris, right? We can prune in this pattern, or in this pattern, or this is repeating this pattern, right? We have a limited amount of choices to prune the neural nets, right? We can also have this vector level pruning, okay? So we either prune the entire 3 by 1 kernel, or we keep it, okay? And next, we have this kernel level pruning, where this entire 3 by 3 kernel, we can either keep it or we prune it. On the right-hand side, that's the other extreme case. We are doing the channel pruning. If we prune away the entire channel. So this CI becomes 1 rather than originally 2 channels in the input. Okay? So we can analyze what is the pros and cons for each choice. Give you 1 or 2 minutes to think about that. What are the pros and cons for this entire spectrum? Which one would you choose if you want to accelerate your neural net on your phone or with specialized accelerator? or on the CPU. Correct. Yeah, exactly. So if you target extreme compression ratio, you want to choose this one. If you have specialized hardware design capability, like you can design ASICs, you can use this approach. But if you want to just target accelerating like on your CPU on a phone, the channel pruning is the best approach. Okay. Question?
What's the advantage of the pattern-based pruning? It doesn't really seem like you get much when you have the like tetra shapes like that.
Okay. So we are repeating several patterns. So you can hard code, for example, this element, this one, these four elements are non-zero. So you can hard code each scenario. For example, these two can share the same kernel, so that you can have very specialized inference engine to deal with that. Okay, very good question. So let's look into some cases, like fine-grained pruning. We have shown these compression ratios ranges from 3 to 12x. Okay, they have usually a larger compression ratio since we have the full flexibility to choose which one to prune. It can deliver some speed up on some customized hardware like EIE, efficient inference engine, but not on the GPU very easily. And then we have this kind of pattern-based pruning, right? Where, for example, NVIDIA has this kind of structured pattern-based pruning with N to M sparsity. Okay, what is N to M sparsity? So out of every M element, okay, N of them has to be pruned. Okay, this appeared in roughly 2020, right? Very modern technique available in A100 GPUs or any Ampere GPUs. Okay, so supporting this 2 to 4 sparsity. So what is 2 to 4 sparsity? For every 4 element, 1, 2, 3, 4, every 4 element, 2 of them has to be 0. Okay, you can have 3 zeros, but you need to have at least 2 of them has to be 0. Okay, so this is 2 to 4 sparsity. Every 4 element, 2 of them, at least 2 of them has to be 0. Okay, and then we can condense this matrix from 8 columns into only 4 columns. Okay, and for each weight, we just need to store a 2-bit indices, okay, indicating the location or indicating whether it is 0 or not. Okay, so for example, for this block, each one we want to associate that with the index indicating the location. Okay, so this is showing the speed up across different neural nets, different data sets, including the image classification, detection, and also transformer with question answering and also machine translation. Okay, so the accuracy is well maintained. For example, the Redsite 50, the dense version in FP16 versus the sparse version in FP16, the accuracy can be well maintained. And similarly for other tasks on the Ampere GPU. So let's look at the other scenario, which is probably the most popular these days. If you want to achieve measured speed up on the CPU on your phone, on the off-the-shelf hardware, okay, which is the channel level pruning. Okay, so channel pruning is basically pruning away the entire channel. Previously, say you have 256 output channels. Now you may have only 200 channels. So from the CPU's perspective, you just have less workload. Okay, so imagine we have 5 layers. We reduce the number of channels, so each layer will become narrower. Okay? And the con is that it has smaller compression ratio, roughly a couple of ranges from 10 to 30% to 50%, rather than like 3x or 10x, right? And compared with uniformly shrinking the number of channels, okay, such channel prune is better then we just uniformly reducing the number of layer with the same sparsity ratio. And we will describe how to choose the optimal sparsity in later part of this lecture.
I had a question actually about the 2 to 4 pattern-based sparsity methods. Like those metrics appear to take advantage of the distribution of important neurons in this layer and important weights. Is there any way to guide training so that you have this relatively flat distribution of important neurons instead of them all
Yeah, that's a good question. Can we enforce such sparsity during training? And the answer is yes. Actually, we'll introduce the regularizations and also the methods to enforce sparsity. A simple way is just to add L2 or L1 regularization, so that during training, all the weights are encouraged to have a small value. So we can either add L1 norm or L2 norm during the training process. Okay, so let's continue to talk about this channel pruning. We experimented the speed up, actually the latency, using two approaches. One is uniformly scaling the number of channels for each channel, okay, just uniformly shrinking each channel, versus do channel pruning. Okay, so with the same latency measured on the mobile phone, we can have higher accuracy, right? Or to achieve the same accuracy, we can have a much lower latency compared with uniform scaling, compared with doing channel pruning, okay, called AMC, AutoML for model compression, okay, which is a push the button solution, feed it with a neural net, and then return a smaller neural net. Okay, so let's now switch gear to determine what parameters should we prune and what neurons should we prune. Okay. So let's start with a simple heuristic. We just want to prune those less important parameters. So this is a purely empirical study in the field currently. Okay, so imagine we have a 3 inputs, x0, x1, and x2, and this is just a one-layer neural net with 3 weights, okay, 10, 8, minus 8, and 0.1. So this is simple one-layer neural net, like Redu, with 10 x0 minus 8 x1 plus 0.1 x2. If you are forced to prune away one of the weights, which weight intuitively will you prune? So for this one-layer neural net, you have 3 inputs, you have 3 weights. The small one. Yeah, the small one, the 0.1. Since roughly after the normalization, each input might have a similar L2 norm. So intuitively, we should prune the weights that has the smallest magnitude. That's also the intuition when I did the experiment in 2015, when I was pruning doing the first experiment. I tried this very simple method and it works super well. And later becomes the magnitude-based pruning, which is widely adopted by industry these days. Okay, so it's turned out such a very simple yet effective method is getting very popular these days. So we just prune small ones. Okay, so imagine we have a weight matrix that has only 4 parameters: 3 minus 2, 1 minus 5. Okay, we just calculate what is the magnitude. Okay, calculate the magnitude. Using the L1 norm, basically getting the absolute value for each weight. Okay, so there are 3, 2, 1, and 5. And then we keep the largest 2. Okay, so we keep 3 and 5 while pruning away the smaller ones, 1 and 2. Okay, so we use this simple heuristic where importance is basically the L1 norm or the absolute value. So this is individual fine-grained pruning. What if we want to do some structured row-wise pruning. We want to prune the entire row. Okay, so we just calculate the L1 norm for each vector. In this case, first row is basically 3 plus 2 absolute value, okay, and 1 plus 5. So we keep the largest one and prune the first row because the L1 norm of the first row is the smallest. There are other heuristics. For example, we can also use the L2 norm, which is in this format. So we can calculate the L2 norm for the first row, okay, L2 norm for the second row, and then compare them. You keep the largest one, prune the smallest one. Okay. And to be more general, we can calculate the LP norm, okay, which is defined in this equation. We can calculate different LP norms. Usually, L1 norm and L2 norms are the most popular criteria when we are doing magnitude-based pruning. Okay, so just now there's a question: during training, can we encourage the neural network to be more sparse? For example, during training time, we have different filters. We have N filters. Can we train them so that some of the filters can easily be pruned? Okay, so we introduce this channel scaling factor. Okay, so before doing convolution, you multiply this filter, every element in this filter, by this scaling factor. Okay, in this case, the first filter will be multiplied with 1.17. The second filter will be multiplied with 0.1, okay? And so on. And then you can apply these regularizations on these scaling factors so that the scaling factors are encouraged to be small. So at pruning time, we just remove away those channels with a small scaling factor. Okay? In this case, we remove filter 1 and filter 2. Okay? So before pruning, we have N filters. Now we removed 2 filters. We have N minus 2 filters in this case. So this is a trainable method that can encourage some of the channels to be closer to 0 so that we can select them and prune them away. Okay? And recently, since last time, we introduced this batch normalization layer, which you just subtract your activation by the mean divided by the STD, and then multiply by this scaling factor at the bias. Okay, so this scaling factor actually can be trained to be smaller to determine the channel scaling factor. Okay, so you add a regularization, L2 norm or L1 norm, on this scaling factor, okay, in the batch normalization layer, which doesn't add you any extra layers or any overhead, which is pretty simple, so that you can determine which channel to prune by using the statistics from this BN layer. All right, so those are magnitude-based, very simple, very effective methods. There are also other approaches, like second-order based pruning method, okay, which we are going to visit with a little bit more equations. Hopefully you're comfortable with that. So we want to minimize the error on the loss function introduced by pruning. Okay, so the introduced error can be approximated roughly by this Taylor series. Okay, so originally the loss is based on W, right, an X input. Now we changed the weight, okay, by delta, since some of the weights are pruned to be 0. Okay, so we perturb the weights, it becomes WP. Okay, since according to Taylor expansion, when we are changing the W by delta W, this is the first order difference. This is the second order difference. This is a cross term, and this is the third order term. Okay, so according to Taylor expansion, the coefficient is basically the first order derivative and second order derivative. Okay? And in the optimal brain damage paper, it assumes that this third order term is pretty small, so we can remove them. And also the first order term is also negligible because the neural net training is basically has converged. So the G, first order G, is close to 0, so we neglect that term. And also the error by for different parameters is independent, so the cross terms is also neglected. So we just approximate the change of the loss function with respect to the pruning of the weights to be the second order derivative. So using this importance score, we can determine which weight should we prune away. So this is the second order derivative in the diagonal matrix of the hedging, the diagonal entries of the hedging matrix, the HII times the square of each weight, and you sum them up together. Okay, so the importance of this weight vector can be represented in that manner. But the overhead is that the hedging matrix is a bit difficult to compute, right? So it's computationally heavy. So just now we talk about those criteria, heuristics to select the weights. What about the neurons? Which neuron should we select when we are doing pruning? Again, we want to prune away those less useful neurons. Okay, and how do we decide which neuron is important? The magnitude-based pruning is also a very good criteria in practice when selecting which neuron to prune. Okay, so this is an example when we have a 4 by 5 weight matrix. Okay, so we have 5 inputs, we have 4 outputs. Okay, when we want to prune away 1 neuron. Okay, so prune 1 neuron corresponds to prune away all the connections associated with this neuron. Therefore, the whole row will be 0. Okay, so that's the relationship between neuron pruning versus synapses pruning or weight pruning. Okay, you prune the neuron, then all the weights, all the synapses associated with that neuron will be get rid of. So this is for a linear layer. What about for this convolution layer? Okay, so we have an input feature map. We have several filters, like 3x3 filters, and then we have several output channels. So if we prune away some of the channels, okay, so if we prune away the second channel, this channel, okay, so the whole filter associated with that channel will be pruned. Okay, and then the next channel is kept. The next channel is pruned again. So the next filter will all be 0. Okay, so that's the relationship between this pruning away the feature map versus pruning away the kernels. Okay, corresponding to here, all the 3x3 convolution filters will be pruned away if this output channel is pruned. So let's look at a detailed example. Okay, so we want to look at the percentage of 0. Okay, POZ, percent of 0 based pruning. So we are using this ReLU activation, which is pretty popular, like we introduced in last lecture. So after ReLU, what happens to the activation? Lots of them will be 0 naturally. Okay, so imagine we have this neural net that has 2 batches. This is the feature of one image. This is the feature of another image. So we have a batch of 2. Okay, so for each image, we have 3 channels. Okay, and the resolution is 4 by 4. Okay? 4 by 4 image, 3 channels. That's a second image. Okay, So how do we decide, are we going to prune this channel, or this channel? Okay. If we prune this channel, since we are considering multiple images, the same pattern has to be applied to the second image since they are in the batch dimension. So this percentage of zero-based pruning is basically looking at what is the percentage of zeros for different dimensions and choose the channel with the largest amount of zeros. So let's look at these three channels separately. So the first channel, what is the percentage of zeros? So we have one image, we have another image. Each image is 4 by 4. Okay, so totally how many pixels? 2 times 4 by 4. Okay, so that's the denominator. And how many zeros are there? 1, 2, 3, 4, 5. Okay, 5 zeros in the first image. How many zeros here? We have 1, 2, 3, 4, 5, 6. Okay, 6 zeros over there. So the percentage of 0 will be 5 plus 6 divided by 32. Okay? 11 out of 32. So that's the percentage of zeros in the first channel. Similarly, we can calculate the percent of zeros in the second channel. Okay? First the image. Okay? So this 5 non-zeros plus 7 non-zeros. So 12 over 32. For the third channel, it will be 14 over 32 by adding them together. So I use this very intuitive illustration rather than using, this can be expressed in one line of code or math equation, right? But I try to make it visualized, so give you more intuition, understanding what is this percentage of zero-based pruning, okay? So this is the ratio for each channel. So in this scenario, which channel should we prune? 1, 2, or 3? Third one, correct. Because the third one has the highest amount of number of zeros, so we want to prune that away. So this is this method using percentages of zero-based pruning approach. So there could be a lot more pruning approaches. After lab 1, feel free to use our starter code to explore different pruning criteria. And then let's introduce another pruning heuristic, regression-based pruning. Okay, so imagine we have this is the input multiplied by the weight, and this is the output. Okay, so instead of considering pruning error of the objective function L, this regression-based pruning try to minimize the reconstruction error of the output. We try to match the output of this layer, layer by layer, okay? This local minimum, this local optimum, okay? So imagine we prune away one row of the weight matrix and prune away one column of the input matrix, okay? So we still obtain this output matrix. So we wanna make sure, try to minimize the difference between the pruned output versus the original output. Okay, so this is a local optimization, since this is just considering the output for this layer rather than the whole neural net. Okay, so in this heuristic, we try to minimize the error between z and z hat. Okay, so z originally equal to x w transpose. Okay, we have four columns in x and 4 rows in w. So the new problem try to minimize z and z hat, the distance between z and z hat. And z hat is basically the sum of different x times w multiplied by this beta c. Okay, so we want to control this beta c, the number of non-zeros in beta c, in beta 0. Okay, and all of them together should be smaller than n. Okay, so which is the number of non-zeros, which is the number of non-zero channels. So we can solve this problem by iteratively, like first fix W, and then we solve beta for channel selection. Okay, and then we can fix beta and solve W to minimize the reconstruction error. So this is the regression-based pruning. Try to minimize the difference of the activation for individual layers by selecting the beta. Okay. All right, so let's dive into a demo to have a summary of today's lecture, including what is pruning, different granularities, criteria to select, right? Which weight should we prune? Okay, so let me switch gear and share the screen for the pruning demo. And many thanks to Eugene, our TA, for making such a wonderful and intuitive demo. So first, we do some setup. Okay, so and then we are going to train. This is a 4-layer neural network. Okay, this is the first convolution layer. One input channel, which is black and white. 3x3 kernel. Okay, and we have 32 output channels. So how many parameters are there in the first layer? We have 1 times 32 times kernel size square. That's 288 parameters, followed by another count 2D. Okay, 3x3 kernel, input channel, output channel. So this is the number of parameters in the second count layer. And then we have a dropout layer, followed by 2 FC layers. Okay, so this is the number of parameters in the FC layer, and we can see the majority of the parameters lies into this first FC layer. Okay, and then we are going to use this simple convnet to work on this MNIST dataset, which contains 10 digits, okay, 0 to 9. We want to classify the digits. And then we are going to pre-train this neural network on the MNIST dataset. Okay, so I'm going to click this button so that it's going to train this model. Okay, so we are going to train it with a learning rate of 1.0. This is learning step, and we are going to train it for 5 epochs. So 5 epochs basically means we are going to go through the data set 5 times. Epoch 1 already finished. Okay, so with only 1 epoch, we can already achieve 98.8% accuracy on this MNIST data set, which is pretty good. Okay, and this is trained on the GPU provided by Google Colab. It's free. Now, by the way, when we are doing homework, our lab assignment will be using similar infrastructure, so you don't have to worry about GPUs or anything. Use this free GPU provided by Google. Alternatively, you can use the premium version of this Colab by just paying $10 per month to enjoy a better GPU that can train faster. So in our case, we already finished these 5 epochs of training, achieving a pretty good accuracy of 99.19%. Okay. All right. So let's first evaluate the accuracy and the model size of this original dense model before any pruning. First of all, can everyone see the screen well? Make sure it's large enough. All right. So let's first evaluate the accuracy of the dense model. It's 99.2%. Okay. So for the digits, the predictions from 0 to 9, they are all correct. And the model size is about 4.5 megabytes. Okay, so this is the original model. And then let's do pruning. Let's do pruning. Okay, so we specify sparsity. We want to prune away 10% of the parameters and see what happens to the prediction. Okay, we are going to call this fine-grained pruner function, okay, which we provided in the starter code. Actually, in the lab 1, you are going to implement this pruner function. Okay, so we just leave you some motivation here. And then we apply this pruning and then try to test what is the accuracy by running this prune model. and then we calculate the model size after pruning. So let's see what is the accuracy after pruning. 99.21, okay, compared with 99.22, almost no loss of accuracy. It's pretty amazing. And you see all the predictions from 0 to 9, they're all correct, actually. It's pretty good. Let's be more aggressive. Let's try prune away 30% of the parameters. By the way, this is without any retraining. We just remove those small parameters, and let's see what happens. Still pretty good accuracy, 99.1%, and all the predictions are correct. Let's try to break it. Someone can give me a larger number.
0.9.
Okay, let's do 0.9. Let's see what happens. Okay, good. You successfully broke the neural net by predicting 3 for digit 1. Okay, so let's see. Although this is 10 times smaller, but it fails to make correct prediction. Let's see how do we solve that. Let's fine-tune the pruned model. Okay, we still have 10% of the parameters left, right? We are not all dead. We still have 10% of the parameters. Let's fine-tune on those remaining 10% of the parameters. Okay, we give a smaller learning rate. Okay, on the parameters. Okay, and then fine-tune them. We are going to fine-tune them for only 2 epochs and see if we can recover the accuracy. Actually pretty fast. 1 epoch has already finished. The accuracy actually recovered to about 97, 98%. And after another round of fine-tuning, it recovers to 98%, okay? Which is a little bit lower than originally, which is 99%, right? But you save your parameters by 10x. Right? So let's make some prediction after this fine-tuning. Okay, so all the predictions are correct in this case. Final accuracy is 98.3 compared with previously is about 99.2. So you lose about 0.9% of the accuracy. Okay. Shall we go more aggressive? Eugene, you name a number that we can't recover the accuracy. 0.95. Okay, let's see. So the accuracy is only about 10%. What does it mean on MNIST? You have 10 digits, you have 10 classes, your accuracy is 10%, meaning that this is just random guess, completely fails, right? So for this one is predicting is 2, for this one is predicting 2, 3, 2, 2. I don't know why it's just like 2 so much. All the images predicted to be 2. At least you get 10% accuracy by predicting everything to be 2. Okay, let's try to fine-tune it by 2 epochs. So after 1 epoch of fine-tuning, it is 96. Another epoch is about 96.76. Okay, so we can evaluate on 10 images. So at least for these 10 images, they are all correct, right? So the model is now 20 times smaller and lose about 3%, 2 to 3% of accuracy. Eugene, shall we go 99%?
I don't know. I never tried.
Never tried. Okay, let's try more aggressive pruning. So as expected, all the predictions is 2, and the accuracy is extremely low. And remember, during the fine-tuning, make sure you are only fine-tuning those survival weights. Okay, don't fine-tune all the weights. Wow, only 42%. This is as expected, right? So we are pruning too aggressively, even after fine-tuning, at least 2 epochs of fine-tuning. we can get only 56%. So half of the guess is correct. So let's see, give it some inputs. And this is 0, this is correct, this is wrong, this is wrong, this is wrong, this is correct. So this is correct. So it looks like it cannot recover from this such aggressive pruning where we are saving 98x smaller model. Okay. So after you go home, feel free to play with the starter code. And in lab 1, we are going to implement such pruning function for you to try different heuristics, try magnitude-based pruning. You can also try hygiene-based pruning. Feel free to play with the notebook. And also this notebook can serve as a playground for you to try other aspects of pruning, right? For example, whether a pruned model can be more secure, can be more robust, can have less bias, whether it can generalize well to a different data set, whether it learns better features, more robust, less bias, right? Those are something you can play with this IPython notebook. Okay, so if you need more GPU resource or if you have other ideas, feel free to come to our office hour or talk to me, and we can explore different stories about pruning. Okay. Okay, so that's all for today's lecture. In next lecture, we are going to talk about how to find the best pruning ratio for each layer. Okay. And what are the better approaches? Why do we reduce the learning rate? What are the best practices to fine-tune it? Can we automate this pruning process by using automated pruning, push-the-button solution? Okay, and talk about some modern research on lottery ticket hypothesis and also system support for different pruning granularities. Okay. All right, that's all for today's lecture. Thank you so much for coming, and hope you have a good day. And I'm glad to take questions.